I wonder if you could use the angles between two mountains to calculate the radius of a planet. And then you wouldn't have to pace off or measure any distance around the circumference of a planet. Any planet, specifically Earth, is going to have cliffs and rivers and oceans and things to make it difficult to measure across them. But if you were to use this method, you wouldn't actually have to pace off any distance around, and that's including the distance between the two mountains. I also wonder how primitive the technology could be to do this sort of exercise. Meaning, would you need modern lasers with great precision, or could you do it with something more primitive, like a primitive clinometer and maybe a more primitive telescope? I don't know. But this is the geometry on how it could be done theoretically. I know this math looks complicated to anyone that's not in the math field, but it's actually just high school trig. So if anybody just has basic math skills of addition, subtraction, and multiplication, they could learn this. And so I doubt that I'm the first one to think of this. I'm sure somebody thought of this 1,000 years ago or longer. So here's the diagram. We have our planet, we have the unknown radius, we have mountain A, mountain B. Ideally, these two mountains need to be far enough apart that you can just barely see one mountain from the other to maximize the distance in between. And the mountains need to be tall enough so that the distance between the tops or the peaks of the two mountains is significantly longer than the distance between the bases of the two mountains. If you were to drop a plumb line through the center of the mountain from its peak down to its base. I've seen a lot of photos of island mountains, I think probably more around the Ring of Fire in the Pacific, where it looks like there may be some mountains that might fit all this criteria. And that's fine if there's a bunch of ocean in between, because we're not measuring the distance in between there. So all you do is stand at the base of Mountain B, shoot an angle straight across with a primitive telescope or a laser. I don't know how modern it needs to be or how precise. And you'll shoot a line here at 0 degrees that goes straight across. This line will form a tangent line to the circle, and you'll hit a specific point here on Mountain A. Climb up to Mountain A and get the height of right there of Mountain A. I did a video on how you can calculate some heights of tall objects. So now that you're standing at this point, shoot a beam back or look back to right where you're standing with a clinometer, and you'll get this angle alpha. This will just be the angle from vertical right here if you're on top. So from the vertical to there will give you angle alpha. While you're standing there, shoot a point back at anywhere along Mountain B here and hit a certain point on Mountain B. It doesn't matter what this angle is, doesn't matter what that angle is. Take your total angle from the vertical, subtract alpha, and you'll get gamma. We know this is 90, we know this is 90. We've calculated alpha and gamma, and we can measure the height of Mountain A and Mountain B up to those points. The interior angles of a triangle have to equal 180 degrees. So we know this is 90, we know that's gamma that we calculated, and then thus we can calculate beta. We use this to find this angle D. So what I've done is drawn two triangles. This triangle here, it's a right triangle, and this triangle here is a right triangle. They are connected by line D. We don't know D, but we know the height of B, and we know beta, so we just take tan beta equals D over B, right there. Solve for D, and you get that. Now let's look at angle alpha here. Cos alpha, this is the hypotenuse, by the way. Here's your right angle. Cos alpha will equal D over A plus R. Cos alpha is D over A plus R. Replace D with all of this, so you get cos alpha equals B tan beta over A plus R. Go through the algebra to solve for R, right there. And then, theoretically, you could calculate the radius of a planet without actually having to measure off any distance around the circumference.